What we're going to look at in this video is the concept of curvature. Very quickly, here are two possible curves. And as you will see, one is curving quite aggressively. Here there's a very sharp turn, and here there's a very slow turn here. So this essentially, this is called the curvature of the curve, is how rapidly or how slowly the curve turns. Essentially. So if you look at this, to try to get an idea or some idea or handle over which one, how we could know what quantify curvature, essentially, if you think about this, the unit tangent vectors, we're not interested in the magnitude of these vectors, but the unit tangent vectors here seem to be saying something very interesting. It seems that if we were to look at the rate of change of these unit vectors, the unit tangent vectors, it would indicate that one might be less than the other or slower than the other. At the same time, if we were to in fact keep things in context, what we would do is we would like to see that change in the unit tangent vector with respect to the curve length, or the arc length, sorry. So keeping that in mind, what we're really trying to say is that we will look at, in fact, the unit tangent vector. So first, let's introduce the unit tangent vector. So the tangent vector we've mentioned before is just r dash of t. So the unit tangent vector is represented by the letter capital T usually, and t is essentially the derivative of a vector function r, given vector function r, and of course that divided by its magnitude would give us the unit tangent vector. So this here is the tangent vector, okay, on its own, right? And this, of course, altogether is the unit tangent vector, okay? So so that's a definition we need to keep in mind. Now let's move further and try to see, now if I go back to the concept of the curvature, what we're saying is that if we could take these are the unit tangent vectors we're talking about. So we're only looking at, now we would look at some kind of a rate of change of these vectors, if you see their behavior with respect to the length of the curve. So in other words, if we were to look at dt ds, okay, where s being the arc length function, and we see how the unit tangent vector is changing with respect to the length, that could give us an idea about or quantify this concept of curvature, this idea of curvature. And since we're not really interested in anything but a magnitude, some kind of size, quantifying it, the rate of change of the unit tangent vector with respect to the curve, arc length, then all we're really interested in is in the magnitude of this derivative. This, in fact, is defined as the curvature. This is called the curvature. So this is the formula for, by definition, the curvature. So the curvature of any curve is essentially the derivative dt ds. So what we're really saying is that we should try to parameterize any vector function with respect to s, and then we proceed to calculate the derivative. Well, mathematically, it is wise to in fact look at a slightly different version of the same formula. If we look at let's go back to this derivative, dt dt. dt dt is simply dt, can be written as dt ds multiplied by ds dt. Now, if you think about it, what we have here is over here. So this implies we can rewrite this as dt ds equals dt dt divided by ds dt. So if I will just on a side note, just to remind you that s by definition is 0 to t, a to t of r dash u magnitude du. Now, if I were to calculate ds dt, clearly that would just be r of t. And you can see why, because integration and differentiation are, of course, antis of each other. So if I were to differentiate this integral, there's no need to integrate it in the first place. So what you get back is simply r dash of t. So that means my formula here can be essentially, this means that dt ds, okay, is equal to, I'm just going to use this notation instead of dt dt, sorry. So that's t prime. And by the way, these are all vectors. The t is a vector here. My apologies. So what you're really saying is, So what you're really saying is t here is divided by, in fact, the magnitude of r prime of t. Okay. So as you can see, that's a much simpler approach, and which means that the magnitude of all of this is, in fact, the magnitude of this, which essentially boils down to just calculating the magnitude of t dash t divided by the magnitude of r dash of t. So as you can see, that is a much easier calculation compared to the other one, the dt ds. So let's go through both these to quickly demonstrate how these work. So here what I've done is the helix example, if you remember, and what I'm doing is simultaneously doing two sides here. So here on this side, what you look at is the r of t is cos t sine t, the original function. Here is the derivative of it. We've done this before. We've already done this as well, which is the reparameterization in terms of the arc length function. So let's proceed. If we were to proceed, this derivative here with respect to s would of course be a 1 over root 2 comes out common, and we end up with this. All right, and if we proceed now to calculate, remember we will first have to calculate the size of this, the magnitude, that's next. And that is equal to square root 2, clearly. All right, so the magnitude of this, on the other hand, is going to be, this is 1. Sorry, this is 1. So it's 1 over square root 2 minus this. That's 1, not 1 over square root 2. Sorry, correction. In this case, that's equal to 1, in fact. The magnitude, I mean. The magnitude of this is equal to 1. Now, the next step, of course, here, we would need t. So t would be r dash, which is, so it will be just 1 over root 2 into minus sine t cos t and 1. Here, of course, t, and this time here it's a function of t here, let's be clear, and here it's a function of s in terms of that parameterization. So it's equal to basically the same thing that you see up. Divided by 1 is just going to give you 1 over root 2 into minus sine s over root 2 cosine s over root 2 and 1. Okay, so here kappa in this case is equal to, now t prime t would mean, let's see here, t prime, if I calculate t prime over here, that turns out to be 1 over root 2 stays inside, and we end up with minus cosine t minus sine t 0. Okay, so therefore the size of that is what we'll put here. So the magnitude of this vector here turns out to be cos square t plus sine square t is 1 plus 0 is 1 square over square root 2. So that's just going to be 1 over square root 2 divided by square root 2, which turns out to be 1 over 2. Here, on the other hand, we are looking at dt ds. dt ds turns out to be 1 over 2 times negative cosine of s over root 2 minus sine s over root 2 and 0. So now when we actually calculate the magnitude dt ds, which is kappa, it's a scalar quantity, of course, is equal to, of course, 1 over 2 into, which will be squared, and then the square root of that, so it'll turn out to be 1 over 2 as well. So therefore, you can see that both lead to the same answer. However, one is, the one on this side this one clearly requires this reparametrization. So if you were to start with RT, here you can proceed directly and finish and get your calculate the curvature. Here, on the other hand, in order to calculate the curvature, you would first have to do the reparametrization. So you'd first have to calculate the arc length function, reparametrize, and then proceed with this R. And you can see the steps here are almost the same as the steps here. However, the extra steps in this are the reparametrization. So it's up to you which method you use, but I would think that this formula is easier and faster to calculate the curvature. We stop here.